In section 11.11, let us discuss the primary motivation behind using power series representations of various functions, and that is approximating these functions by the power series. So suppose that a certain function can be represented by a power series. So let's say f of x is equal to its Taylor series at the point a for some fixed real number a. And so this means that f of x can be represented as this Taylor series here. Let us recall the notation for Taylor polynomials. So the reason we want to talk about polynomials and not infinite series, of course, is that we cannot effectively sum up infinite number of terms. So what we can do, though, is we can approximate an infinite sum with a sum that contains finitely many terms. So to us, a Taylor polynomial is the nth partial sum of this Taylor series. And so this is what we call Taylor polynomial. The Taylor polynomial of degree n. It's easy to see that the highest power that occurs in this sum, oops, this should have been n over here, the highest power of x that occurs in this sum is n, and so we can say that this is a Taylor polynomial of degree n of the function f of x. And so, of course, this is also the nth partial sum of the Taylor series. So we cannot sum up the infinite power series. We can, though, consider this finite polynomial. So for finite polynomials, we can evaluate their terms, their values at any point. If we have a, say, computer that can perform additions and multiplications. So if we have such a computer, then additions and multiplications are enough to evaluate such a Tn of x at any x. So if we also know that this Tn of x goes to f of x when n goes to infinity, then we can approximate the value of f at some point x by the value of this T of n at this point x. So let's say we want to determine what is the value of f for some x. We say, well, we cannot really sum up an infinite series. So what we can do is we'll pick an n large enough so that we expect that f of x is approximated by Tn of x at that point x, and then just evaluate the value of the polynomial at the point x. And then say, well, that's an approximation of f evaluated at this point x. So how big an error we are making? So obviously we're making some error, right? So we're discarding the tail of this power series, everything that comes after the term number n. All these terms are not taken into account when we make this approximation. So the error we make in this approximation meaning this one where we said that f is approximately Tn. This error is something we have actually talked about already, and it is given. This error is given by, or let's say this error is estimated by the Taylor's inequality. So it just happens to be that everything in this topic carries the name of Taylor. And here is the inequality. We have already seen it before. It says that if we know that the n plus first derivative of f is bounded by a constant, let's say m, then the error we are making, which is defined as the difference between the true value f of x and the approximated value Tn of x. And so this error is at most m divided by n plus 1 factorial times x minus a to the n plus 1. So this is a formula we have already used before. Now it will be employed to estimate the goodness of approximation of f by its Taylor polynomial Tn of x. So let's take an example. Something that would be interesting to do perhaps is approximate a function, say f of x equal to cubic root of x. So this is a function that's rather non-trivial to evaluate. And let's say we, for some purposes, let's say for some engineering purposes, we're interested in its values around the point a equals 8. So we will approximate the cubic root of x about this point. Of course, at the point a, we do know the value of the cubic root. It's just 2. So what we're interested in is the values of f around this point a with a known value of f. So we have a single point somewhere, right? Here's our 8, and we do know value of our function at this particular point, but we would like to determine what are the values of f around the point 8. Okay, so how are we going to do it? We will use the Taylor polynomial of this function of degree 2. So we'll use the quadratic polynomial and approximate f of x with this quadratic Taylor polynomial. And secondly, let us, after we obtain this approximation, estimate the accuracy of this approximation. So since our intention is to use the Taylor polynomial of degree 2, it means we need to recall the formula for t sub 2. Right, so the Taylor polynomial of degree 2. So by the formula we have over here, with n equals 2, we have t sub 2 equals f at the point A, so this is the 0th term, plus f prime of A divided by 1 factorial times x minus A, plus f double prime at A over 2 factorial times x minus A squared. So this is a polynomial of degree 2, and so here we have it, t sub 2 of x. We will need the values of f and its first two derivatives at the point A. A equals 8, so we may just as well replace the a's everywhere in this polynomial with 8. So let's go ahead and do that. So I have 8, 8, 8, 8, and 8 here. Great. So let us evaluate derivatives of f first. We know that f of x equals x to the power 1/3. F prime of x then is 1/3 x to the minus 2/3. And f double prime of x is 1/3 minus times minus 2/3 times x to the power minus 2/3 minus 1, so that would be minus 5/3. And then we will need, for the estimate of the error, we'll need the next order derivative, right? According to the Taylor inequality here, we need to deal with the next derivative, with the third derivative in our case. So let's go ahead and evaluate f triple prime of x, which is 1/3 times minus 2/3 times minus 5/3 times x to the minus 8/3. Great. So it means we can at this point evaluate the values of f and its first two derivatives at 8. So f at 8, of course, is just 2. It's a cubic root of 8, giving us 2. F prime at 8 is 1/3 x to the minus 2/3. So that is x to the 1/3 to the power minus 2. X to 1/3 gives us 2, and then raising 2 to the power minus 2, we get 1/4. And so f prime at 8 is 1/12. F double prime of 8 now is, this expression here is x raised to the 1/3, which is 2, raised then to the power minus 5. That would be 1/32. So we have minus 2/9 times this should be 9, minus 2/9 times 1/32. So 1/32 here comes from the x to the power minus 5/3. And this can be simplified further, giving us minus 1/9 times 16. And so 9 times 16 is 144. So here we get that f double prime of 8 is minus 1/144. Great. So we have successfully computed the values of f and f prime and f double prime at 8. So we're ready to write down t2 of x. And that will complete the first part of this example. So we have that t2 of x equals, so first let's write the formula again, plus f prime over 1 factorial x minus 8 plus f double prime at 8 over 2 factorial times x minus 8 squared. And so with our evaluated with the values that we get for f and its derivatives, we have 2 plus 1 12th x minus 8. The 1 factorial in denominator just gives us 1. So plus f double prime at 8 over 2. 2 factorial just gives 2. So that would be 1 over 144 with the minus multiplied by 1/2 for the 1 over 2 factorial multiplied by x minus 8 squared. And so finally the answer is the following quadratic polynomial. It's 2 plus 1/12 x minus 8 minus 1 over 288 x minus 8 squared. So to summarize, we have just shown that cubic root of x is approximately t2 of x, which is equal to 2 plus, which is equal to this expression here. And this approximation holds when x is close to 8. So we have this expression, this quadratic polynomial, when x is close to 8, which is a rather remarkable thing, because see, this cubic polynomial, a cubic root here that we need to compute is a rather non-trivial function. It's not just addition and multiplication or combination of these, and yet we can approximate it really well by this quadratic polynomial, which only involves addition and multiplication, well, also division right here, assuming that x is close to 8. So if our arguments are sufficiently close to 8, this may be a very good approximation of the function cubic root of x. Now, how good an approximation is it? To answer this question, let us use the Taylor's inequality again. So this would be the second part of our question. So using the Taylor's inequality, which was, let me remind you what it said. So it says that f of x minus tn of x is at most m divided by n plus 1 factorial times x minus a to the n plus 1, where m is a constant such that the n plus first derivative of f is at most m. And so let's use this inequality. So we will approximate f of x when, of course, we have to set x to be close to 8. How close is the question? Well, let's use the interval between 7 and 9. That is to say, when x minus 8 is at most 1. Right? So on this interval between 7 and 9, what can we say about the third derivative? Right? So we are working with this interval. We have n equals 2, since we have the second order Taylor polynomial n is equal to 2. So the question is, what is a suitable value for the constant m? How can we estimate the third derivative of f? So to do that, let's go back to where we computed the third derivative. We did it right here. And let us use this formula to obtain an estimate now. So we have this formula for the third derivative of f. So according to this formula, f triple prime of x is equal to 10 divided by 27 times x to the minus 8 thirds. So we want to bound absolute value of f triple prime of x with a constant m when x is between 7 and 9. Alright, so let's look at the expression we have here. We have triple prime of f of x, which is, when you apply absolute value to it, is the absolute value of 10 over 27 x to the power minus 8 thirds. So this is the 10 over 27 times 1 over x to the 8 thirds. And we want to estimate this expression when x is between 7 and 9. Now, in order to obtain such an estimate, what we have to say is the following. So since x to the 8 thirds is increasing function, right? We have x to a positive power, so this is increasing. The denominator here is smallest, so we're interested in the smallest value for the denominator because that makes the entire expression the largest. I should also note that we dropped the absolute values here because x is positive, so everything in here is positive, of course, in this expression. So x to this power is increasing, so denominator is smallest when x equals 7. Right? So we are looking at the interval between 7 and 9, and on this interval, denominator is the smallest for x equals 7. So that's when the right-hand side in this equality is the largest. And that's what we're interested in. We want to find the largest value of the third derivative so that you can bound it like so. If we can find the largest value, we'll just put here this largest value in place of m, and then the inequality for the third derivative will be true, like so. So that's when the right-hand side in this equality is the largest. Great. And so we know, therefore, that f triple prime of x is at most 10 over 27 times 1 over 7 to the 8/3. Okay. Now this number, this power here is unpleasant to evaluate. 7 to the 8/3. It's hard to determine what that number is. So let's estimate this number as well. So 8/3 is bigger than 2. Okay. So this power here is bigger than 7 squared. Right? It has the exponent is bigger than 2. So by replacing 8/3 with 2, we have a smaller number, and so this ratio is at most 10 over 27 multiplied by 1 over 7 squared. And so this is a nicer number in the sense that evaluating it does not require taking cubic roots. So we can just evaluate this number with a computer that can only multiply and divide. So in this sense, it is a better expression here. And so once I perform the multiplication, I will get 10 divided by 1323 here. So that's the value that that I obtain if I multiply the factors in the denominator. And so great, I now have a number which works for m. Right, so this here I can set to be my m. So this is the constant. I can set m to be equal to, right, this m over here. So then, according to the Taylor's inequality, I have, let me pull up the Taylor's inequality right here. All right, and we use it for n equals 2. And now we know which value we can take for m. It's the one that we just obtained over here. So let's go ahead and substitute everything into our into the Taylor's inequality. So we have now that f of x minus t2 of x is at most 10 over 1323 multiplied by n plus 1 factorial. So this would be, recall that n is 2, so this is 3 factorial times x minus 8, since a is 8, to the power 3. And because we're looking at the interval between 7 and 9, this difference is at most 1, so I have the left-hand side being at most 10 over 1323 times 6. And if I multiply these together, I will get 7938 in the denominator and 10 in the numerator. So that is approximately 0.00126. And so we can approximate our function with the precision 0.012.6. So we can evaluate cubic root of x with this, with at most this error on the interval between 7 and 9. Now, to give you an idea about how good an approximation this is, let us see how this error measures up to the graph of our function, right? So we have the function that is being approximated by this polynomial over here. Now, how good an approximation is this? So to get an idea, let us look at the plot of these two functions side by side. So here we have in blue the graph of the cubic root of x plotted here on the interval between 0 and 12, and in red we have the quadratic polynomial shown here. So this is the T2 that we obtained, and as you can see, not only on the interval between 7 and 9, which are roughly over here, but in fact also between say 6 and 10, the two graphs are virtually indistinguishable from each other. They are sitting so closely on top of each other here. So in fact, our quadratic polynomial gives a pretty good approximation of the cubic root of x close to 8. Now, we could have used an even higher degree polynomial, say cubic or fourth degree polynomial, and we would get an even better approximation to the cubic root of x. And so whenever you have a computational or an engineering application that requires computing roots or say trig functions, all of these applications, all of the software that you may use does not actually, well, for the most part, it's not actually using any fancy method. What it does is it approximates the function that you want to compute with a polynomial, just like we did in this example here. And so we have answered the part B, which asked to estimate the accuracy of this approximation, and this completes example 1.